Fetch and add. One final hardware primitive is the fetch and add instruction, which atomically increments a value while returning the old value at a particular address. So it does this simultaneously or atomically. It increments a value while at the same time returning the old value at a particular address, like this. Int, so we still use int to initiate it, fetch and add with the argument int asterisk ptr. Inside this int old equals asterisk ptr semicolon and asterisk ptr equal old plus 1 semicolon. Then next line return old semicolon closing curly bracket. Type def struct underscore lock t. Inside this is int ticket and int turn closing semi bracket lock t semicolon. Then we initialize void lock, so void lock underscore init argument lock underscore t asterisk lock. Inside this is lock to ticket equals to 0 semicolon. Next line lock to turn equals to 0 semicolon closing semi curly bracket. Void lock argument lock underscore t asterisk lock. Inside this is int my turn equal fetch and add argument end lock to ticket semicolon, while argument lock to turn not equals to my turn, next line semicolon slash pin closing semi curly bracket. And then void and lock argument lock underscore t asterisk lock, then lock to turn equals to lock to turn plus 1. So that's the ticket locks. In this example, we'll use fetch and add to build a more interesting ticket lock. Instead of a single value, this solution uses a ticket and turn variable in combination to build a lock. So it uses a ticket and turn variable to build this lock instead of just single value. So this basic operation is pretty simple. When a thread wishes to acquire a lock, it first does an atomic fetch and add on the ticket value. So it fetch it just like so since it increments at the same time return the value to the old address. So when a thread wishes to acquire or get a lock, it first does an atomic fetch and add on the ticket value. So it fetch it or it returns it and add on the ticket value. That value is now considered his thread's turn. So after it does that atomically, now that value is now considered this thread's turn, or it's my turn, which is this int my turn equals to fetch and add with an argument and lock and ticket. The globally shared lock to turn is then used to determine which thread turn it is. So this end lock to turn is then used to determine which thread turn it is. When my turn is equals to equal turn for a given thread, it is that thread's turn to enter the critical location. So that if that's equal, therefore that's turn to enter the critical location. But if not, so it will need to spin in this while loop. While lock to turn is not equals to my turn, spin. So unlock is accomplished simply by incrementing the turn such that the next waiting thread, if there is one, can now enter the critical section. So you may think that Those int actually simultaneously increment it here. Asterisk ptr equals to old plus 1 and then return old. So it doesn't use an if else, but it used the equal sign, just like the first example of hardware support. But in unlock, actually after we've done that, we fetch and add the ticket value inside our lock code. Now, unlock is accomplished by incrementing the turn such that the next waiting thread, if there is one, can now enter the critical section. So here, turn plus 1. So if there's another thread that's waiting, or if not, it's still okay. But this unlock handles that using the turn plus 1. Note one important difference with this solution versus our previous attempts. It ensures progress for all threads. So kind of like achieving now the fairness. Once a thread is assigned its ticket value, it will be scheduled at some point in the future. So once we fetch and add a value to that thread using that int myTurn, it will be scheduled at some point in the future once those in front of it have passed through the critical section and release the lock. So once the first in the queue finish it. So in our previous attempt, no such guarantee existed. A thread spinning on a test and set, for example, could spin forever even as other threads acquire and release the lock. So the test and set example we have actually do not guarantee that that ensures progress for all threads, or that ensures like no spin lock. So in test and set, for example, it could spin lock or spin forever even as other threads acquire and release the lock. So even if other threads are asking for that. So in this case, we avoid that by making sure that all of those that fetch and add will be given their time or turn. Because after unlock, those next in turn will be next. So tip aside, less code is better. Programmers tend to brag about how much code they wrote to do something. Doing so is fundamentally broken. What one should brag about rather is how little code one wrote to accomplish a given task. Short, concise code is always preferred. It is likely easier to understand and has fewer bugs. As Hugh Lower said when discussing the construction of the pilot operating system, if the same people had twice as much time, they could produce as good of a system in half the code. So you double the time, you make the code less. You clean half of it. So next time you're bragging about how much code you wrote to finish the assignment, think again, or better yet, go back, rewrite, and make the code as clear and concise as possible. Too much spinning? What now? Our hardware-based locks are simple. Only a few lines of code we define via int. You can even prove that if you'd like to by writing some code, which are two excellent properties of any system or code. So it works. You can even try that by writing some code which is achieves the correctness property we want to achieve early on. The second thread, however, in some cases, this solution can be quite inefficient. Imagine if you're running a thread on a single processor. Now imagine that one thread, thread 0 is in a critical section and thus has a lock held and unfortunately gets interrupted. The second thread, thread 1, now tries to acquire the lock but finds that it is held. Thus it begins to spin and spin. Then it spins more. And finally, a timer interrupts goes off. Thread 0 is run again, which releases the lock. So again, the second thread, thread 1, now tries to acquire the lock, but finds that it is held. So again, the second thread, thread 1, now tries to acquire the lock, but find that thread 1, thread 0 held it. That it begin to spin and spin. Then it spins some more, and finally a timer interrupt goes off. Thread 0 is run again, which released the lock. So in the previous chapter, we make sure that in this fetch and add value, we reduce that spin lock because some interrupt could interrupt that thread and run the other thread, right? So here's what it meant. So the second thread 1, now tries to acquire the thread 0 or remove the thread 0 because timer interrupt goes off. So thread 0 is run again, which releases the lock. So and finally the next time it runs, says thread 1 won't have to spin so much and will be able to acquire the lock. Thus, any time a thread gets caught spinning in a situation like this, it wastes it wastes an entire time slice doing nothing but checking a value that isn't going to change. So again, and finally, the next time it runs, see, thread 1 won't have to spin so much and we will be able to acquire the lock. So since the thread 0 was interrupted, like when the now thread 1 tries to run on that critical section, it won't have to spin again because thread 0 released that already and will be able to acquire the lock. Thus, anytime a thread gets caught spinning in a situation like this, it twists an entire time slice doing nothing but checking a value that isn't going to change. So this is the entire problem we're gonna solve using OS or software. We're gonna try to minimize the spin because as we will later see, these spin are actually sometimes helpful if the lock is about to release. So this fetch and add actually solve the spin lock problem via interrupt. So it's this hardware support like solve that. But the question is, how do we minimize this spin? So that's what we were gonna solve through OS. So the problem gets worse with n threads containing for a lock. n-1 time slices may be wasted in a similar manner, simply spinning and waiting for a single thread to release the lock. Hardware support alone cannot solve the problem. We'll need OS support. Let's now figure out just how that might work. So the crux, how to avoid spinning. How can we develop a lock that doesn't needlessly waste time spinning on the CPU? A simpler approach, just yield baby. Hardware support got us pretty far. Working locks, and even as with the case of the ticket locks, fairness in lock acquisition. So these ticket locks, like the turn, actually there's fairness because you're able to interrupt that in a specified turn, in an equal turn. So it achieves the fairness using the fetch and add. or turn and value used, or turn and ticket used in acquisition. However, we still have a problem. What to do when a context switch occurs in a critical section and threads start to spin endlessly? Like, we need to reduce that spin while waiting for other thread to enter that critical section. Though you achieve the fairness, but you still don't control the spin. There's still a spin that could be, let's say you achieve a fairness through equal sharing through the turn value. So each thread has this specified turn. But what about the spin they wait, like the number of spin they do? Like for example, 10 spin for in each thread. So those 9, if we could reduce that to 1 spin, then we could use that 9 spin of CPU to other work. So, and the threads start to spin endlessly, waiting for the interrupted lock holding thread to be run again. So lock with test and set and yield. So here are the solutions. So we still use test and set. So we like take advantage of test and set hardware support, but we use another software primitives, which is yield. So our first try is a simple and friendly approach. When you're going to spin, instead give up the CPU to another thread. So instead of waiting via spinning, give up the CPU to another thread. So in this approach, we assume an operating system primitive yield. So we assume this yield function from OS, which a thread can call when it wants to give up the CPU and let another thread run. So these are supported by the OS already. So this function or a thread can be in one of 3 states: running, ready, or blocked. Yield is simply a system call that moves sorry, yield is simply a system call that moves the caller from the running state to the ready state and thus promotes another thread to running. So again, a thread can be one of 3 states: running, ready, or blocked. Yield is simply a system call that moves the caller from the running state to the ready state and thus promotes another thread to running. So it just changed the state from running to ready. Thus the yielding thread essentially the schedule itself. So you may like imagine now how we would do that in the OS. Of course, we will use an interrupt or the signal, right? Because that's how we use it before when changing from ready to running state. So that's the yielding thread, essentially the schedules itself. So if a thread happens to call lock and find a lock held, it will simply yield the CPU. So it will simply sleep itself and then yield the CPU, and thus the other thread will run and finish its critical section. In this simple case, the yielding approach works well. So let's just so that are the simple application or the problem and the solution or the solution for that simple problem. Now let us consider the case where there are many threads, say 100 contending for a lock repeatedly. In this case, if one thread acquires the lock and is preempted before releasing it, the other 99 will each call lock. find the lock held, and yield the CPU. So again, let us now consider the case where there are many threads, say 100, contending for a lock repeatedly. In this case, if one thread acquires the lock and is preempted before releasing it, the other 99 will each call lock, find the lock held, and yield the CPU. So there's a lot of thread that will deschedule itself or sleep itself. So assuming some kind of round robin scheduler that are tasked to deal with that, each of the 99 will execute this run and yield pattern before the thread holding the lock gets to run again. So if you want to change the state from that critical section to running state, this thread needs to wait for that 99 to deschedule or sleep itself. Well, better than our spinning approach, which would waste 99 times slices spinning for all of that, which 100 slice, 1000 slice. Sorry, 99 times 100. Yeah, it's 1000 slice. We will just need to waste 100 slice. So worst, this approach is still costly, right? The cost of context switch can be substantial, and there is thus plenty of waste. Whereas this approach does not address starvation, a thread may get caught in an endless yield loop while other threads repeatedly enter and exit critical section. So again, whereas this approach does not address starvation, a thread may get caught in an endless yield loop while other threads repeatedly enter and exit the critical section. So yeah, it doesn't address the fairness because we don't have a way to prioritize those 100 queues. So though it solved that for 2 threads, for this 100 threads for a context switch, and then for fairness, it doesn't do any good. So using queues, sleeping instead of spinning. The real problem with the yield is actually still sleeping, but it's not like systematic or a strategic way to take advantage of the CPU cycle due to the problem of context switch for a lot of threads. Now we will solve that lot of threads problem using some queues, so to achieve the fairness for that, but we will still use the same concept, which is the one we solved using the basic problem, which is the sleeping, right? So the real problem with some previous approaches, other than the ticket lock, is that they leave too much to chance. So the scheduler determines which thread runs next. So they leave, again, the OS mostly determine the one that runs next, right? So again, our purpose of creating this thread library is for the programmer to be able to control, despite the OS working condition or scheduler, how our program will run. So the scheduler determines which thread runs next. If the schedule makes a bad choice, a thread that runs must either spin, waiting for the lock, our first approach, or yield the CPU immediately, our second approach. So if the scheduler makes a bad choice, a thread that runs must either spin, waiting for the lock, which is our first approach, or yield the CPU immediately, our second approach. So there's an advantage and disadvantage on those, and we will gonna use both, like the hard grid approach again, to take advantage of their efficiencies. So for the spin waiting, it could be good if we're gonna wait one cycle before we yield it. So instead of yielding, yield is better after we've done wait for one cycle, because a cycle could be good if we're actually doing it for only one time or one cycle or as less as possible, right? So thus we must explicitly exert some control over which thread next gets to acquire the lock after the current holder releases it. So again, we must explicitly ex- exert some control over which thread next gets to acquire the lock after the current holder releases it. So that's where the priority queue, it solves those problems. To do this, we will need a little more OS support as well as queue to get to keep track of which threads are waiting to acquire the lock. So we need to track it using the OS support, and we need queue to prioritize it. For simplicity, we will use the support provided by Solaris. So instead of creating our own queue and tracking tool, we will use the tool provided by Solaris. So in terms of two calls, so park to put a calling thread to sleep, and unpark to wake a thread ID to wake a particular thread as designated by thread ID. So we will gonna use a thread ID to sleep and wake that. So that will help us to prioritize and track it. So these two routines can be used in tandem to build a lock that puts caller to sleep. If it tries to acquire a held lock and wakes it when the lock is free. So again, these two routines can be used in tandem to build a lock that puts a caller to sleep. So again, these two routines can be used in tandem to build a lock that puts a caller to sleep if it tries to acquire a held lock. Yeah. So basically, the use of this routine are actually to put the next thread. I mean, you're gonna track the thread. For example, thread ID 1 request a lock that is currently held. So these routines are used to lock that, um, to sleep that, and then since you track it via thread ID, you can wake that same person via priority after the lock is withheld or released, and makes it when the lock is free. So let us look at the code in figure 28.9 to understand one possible use of such primitives. So these are the primitives for this type of use. So these are the more modern or more realistic approach or more realistic implementation of thread library. So type def struct underscore lock t. Inside this is influg semicolon, next line int guard semicolon, next line q underscore t asterisk q semicolon, and then semi-curly bracket and lock t semicolon. Now next line, void lock underscore init, argument lock underscore t asterisk m. Inside this is m to flag equals to 0 semicolon. Next line m to guard equals to 0 semicolon. Next line is q init m to q semicolon, and then closing semi-curly bracket. So that's how you initialize this. So you After you set the variable or initialize the variable flag and guard, you queue init m to q, and then closing, and then this is the lock and unlock code. So void lock argument lock underscore t asterisk m, inside this is while test and set m to guard comma 1 equals to 1. So and the next line semicolon, this means this line while means acquire guard lock by spinning. So it acquired the guard lock by spinning. So if m to plug equals to 0, then inside this it means that flag inside this is m to flag equals to 1, meaning we acquire the lock, and then m to guard equals to 0. So after we apply the lock, m to guard will be we put the guard back to 0, and then else inside of else is q add m to q get id, so we get the id to track it, and then m guard initialize initially it equals to 0, then park semicolon, and then close semicolon curly bracket in this else, and then close this entire lock function. So as you can see, after we get the track id, we put the guard, initially is 0, but it increment of course as we prioritize, right? Because we initialize q init like m to q. So yeah, so we put that into q, basically we track that, and then we park it, so we slip it basically. So void unlock argument lock underscore t asterisk m. So inside this is while again, test and set m to guard comma 1 equals to 1. Next line semicolon, acquire guard lock by spinning. So next line, you acquire the guard lock by spinning. Now next line, so as you can see, we acquire the guard lock by spinning. So it's kind of like we increment it. So if q empty m to q, next is m to flag equals to 0. Let go of lock, and no one wants it. So if q empty m to q, next line m to flag equals to 0 semicolon. Let go of flag, no one wants it, else unpark. So q remove m to q semicolon, hold lock, and then / for next sorry, let me repeat, void underscore unlock argument lock underscore t asterisk m, inside this is while test and set m to guard comma 1 equals to 1. So it means again acquire guard lock by spinning. So this is what we mean by this, we acquire the guard lock by waiting, by spinning, like waiting. If q empty m to q, then m to flag is equals to 0. Let go of flag, no one wants it. So what that does if means, if q is empty, then we set the flag to default, which is 0, because no one wants it. Else unpark. So else unpark, which means we wake up. So q remove m to q, hold lock for next thread, then m to guard equals to 0, closing semi curly bracket. So first, what does this mean? Let us check this code by code. So first, we combine the old and test set idea with an explicit queue of lock waiters to make a more efficient lock. So these are the queue waiters we initiate to make a more efficient lock. Second, we use a queue to help control who gets the lock next and thus avoid starvation. So here, you might notice how uh, the guard is used when it basically is a spin lock. So we use the guard as a spin lock. Like here, if m to flag equals to 0, m flag equals to 1 inside it. So lock is required basically as a spin lock around the flag and q manipulations the lock is using. So it's here else q m to q get id m guard equals to. So that's how guard is used. So this approach doesn't avoid spin waiting entirely. A thread might be interrupted while acquiring or releasing the lock. So not just while acquiring that this thread might be interrupted. So it doesn't remove the spin, but it lessens it, like the problem we want to solve earlier, and thus cause the other threads to spin with. So even if releasing it, it actually spin just one before it let it go. Like this, the m to flag equals to 0, let go of lock. So if qf empty, so that's another spin. However, the time spent is spinning is quite limited. So the spinning is not in the critical section, but in the if q empty, m to q in release, and in this is f and m is to flag equals to 0, m flag 1, lock is acquired. So just a few instructions inside the lock and unlock code instead of the user defined critical section. So instead of putting it in critical section, these however, the time spent spinning is quite limited. Okay. So here, void lock, argument lock underscore t asterisk m. Inside this is while test and set m to guard comma 1 equals to 1. So acquire guard lock by spinning. So these are the code that used to spin it. So you might also observe that in lock, when a thread cannot acquire the lock, it is already held. We are careful to add ourselves to a queue by calling the getID function to get the thread ID of the current thread. So again, you might also observe that in lock, when a thread cannot acquire the lock, it is already held. We are careful to add ourselves to a queue. So if the lock cannot be get by the thread, we add that or add ourselves to the queue by calling the get ID first. So here is the code for that. So else q add mg get id function to get the thread ID of the current thread. So that's how we get the thread ID of the current thread. Then set the guard to 0 to yield the CPU. So this is actually how we yield the CPU. So guard equals to 0, else q add to get ID, and then yield, and then park. So a question for the reader, what would happen if the release of the guard lock came after the park and not before? Hint, something bad. So after so this is how we yield the lock. So what if we release the lock first before we slip it? Something bad will happen, because again we acquire that here while test and set m guard equals to 1, acquire guard lock. Now if m flag is equals to 0, meaning that no one is in the critical section, we put that flag equals to 1, so lock is acquired, and then m guard is reverted to 0, or we yield the guard. Else q add m to g get id m guard. So you might further detect that the flag does not gets set back to 0 when another thread gets woken up. So the flag does not get set back to 0, or the free for other threads to enter critical section when another thread gets woken up. So why is this? Well, it's not an error but rather a necessity. When a thread is woken up, it will be as if it's returning from park. So however, it does not hold the guard at that point. So the reason why it's not the flag does not return to 0, because when you wake up a park, it's like waking it from sleeping. So however, it does not hold the guard because it released that. So thus cannot even try to flag to 1, so 0 wouldn't work as well. So it cannot even try to set the flag to 1 or to enter the critical section. Thus, we just pass the lock directly from the thread, releasing the lock to the next thread acquiring it. So therefore, what we do is we just pass the lock from the thread releasing it to the next lock. Using priority queue, flag is not set to 0 in between. So the flag is not set to 0 in between there. We just pass the lock. So it's kind of like magic, right? We just pass the lock instead of making it 0 available for anyone. So finally, you might notice the perceived race condition solution just before the call to park. Again, finally, you might notice the perceived race condition in the solution just before the call to park. So with just wrong timing, so this could be a race condition if we put park first before the guard. With just the wrong timing, a thread will be about to sleep first. So again, with just the wrong timing, a thread will be about to sleep first or park before the guard is set to 0, assuming that it should sleep until the lock is no longer held. A switch at that time to another thread, say a thread holding the lock, could lead to trouble. For example, if that thread then released the lock, the subsequent park by the first thread would then sleep forever because those are interconnected. So the first thread will sleep forever, a problem called wake up or waiting race. So that's the problem. It will get stuck. So that's why you get this indeterministic result in computers, right? So Solaris solved this problem by adding a third system call, setPark. So by calling this routine, a thread can indicate it is about to park. So here, setPark. It is about to sleep, basically. So if it then happens to be interrupted and another thread wakes the first thread, so again, if it then happens to be interrupted and another thread wakes the first thread, before the sleep or park actually called before the M guard equals to 0, the subsequent park returns immediately instead of sleeping. So here's what the set park means. Instead of sleeping it forever, it returns that to the queue immediately. So different solution could pass the guard into the kernel. So different solution in this would be to pass to this like wake condition is to pass the guard that it acquired to the kernel. In that case, the kernel could take precautions to atomically release the lock. Take precautions to atomically release the lock and dequeue the running thread. To atomically release the lock and dequeue the running thread. Again, the kernel could take precautions to atomically release the lock and dequeue the running thread. So again, a different solution could pass the guard into the kernel. In that case, the kernel could take precautions to atomically release the lock and dequeue the running thread. So it will release the lock and will dequeue the running thread instead of sleeping it forever. So it will release that to that thread instead of sleeping it forever and then dequeue it. So different OS, different support. We have thus far seen one type of support that an OS can provide in order to build a more efficient lock in a thread library. So that's one kind of support in Solaris to build a more efficient lock library in a thread library. Others, like Linux, provides a Vuetex, which is similar to the Solaris interface, but provides more in-kernel functionality. Specifically, each Vuetex has an associated with it a physical memory location. So this Linux lock library provides more in-kernel functionality. So this Vuetex, the reason why it has kernel functionality, because these Vuetex or lock are associated with a specific memory location. So it also provides per Vuetex in kernel queue. So it also provides per Vuetex in the actual kernel queue. So callers can use Vuetex calls to sleep and wake as need be. So aside from having this memory and internal queue from kernel, it can also wake and sleep as need be. So here Linux-based Vuetex. So we create a void mutex underscore lock with a parameter int asterisk mutex. Inside this is int v semicolon. So bit31 was clear. We got the mutex fast path. So if atomic bit test set mutex comma 31 equals to 0, then return next line return semicolon, next line atomic increment mutex semicolon. While 1 inside it, if atomic bit test set mutex comma 31 equals to 0, inside this atomic decrement mutex, the next line return semicolon, closing semi-curly bracket. Then have to wait first to make sure Vuetex value we are monitoring is negative lock, so v equals to asterisk mutex. If v is greater than or equals to 0, next line continue semicolon, then Vuetex, next line Vuetex wait argument mutex comma v, closing semi-curly bracket, closing semi-curly bracket. Then void mutex underscore unlock. Inside this is int and asterisk mutex, and then adding 0x, next line adding 0x 800,000 to counter result in 0 if and only if there are not other interested threads. So if inside this void mutex underscore unlock argument in asterisk mutex, we have if atomic add 0 argument mutex comma 0x 800,000 closing parenthesis, next line return semicolon, then Vuetex wake, next line Vuetex wake argument mutex semicolon. So this line means there are other threads waiting for this mutex, wakes one of them, and then close semi-curly brackets. So specifically, two calls are available: the call to Vuetex wait address, and then the expected. So this call like mutex address and then the expected puts the calling thread to sleep, assuming the value of the address is equal to expected. specifically two calls are available. The call to Futex wait, so here Futex wait, we have an address and the expected, which puts the calling thread to sleep, assuming the value at the address is equal to expected. So that's what it means. Futex wait mutex comma v. So if it's not equal, the call returns immediately. So it will only put it to sleep if the address, assuming the value at the address is equal to expected. If it's not equal to expected, the call returns immediately if it's not equal. So the call will return. So the call to the routine Futex wake address. So here wake mutex wakes one thread is with the call to the routine Futex wake address wakes one thread that is waiting on the queue. So this code snippet, so as you can see, it only has what argument? The wake. So the code snippet from low level lock.h in the NPTEL library is interesting for a few reasons. First, it uses a single integer to track both whether the lock is held or not, the high bit of the integer, and the number of waiters on the lock, all the other bits. So it only uses a single integer to track it instead of the get ID, whether the lock is held or not, the high bit of the integer, and the number of waiters, which is the Futex wait. Second, the code snippet shows how to optimize for the common case, specifically when there's no contention for the lock, with only one thread acquiring and releasing a lock. Very little work is done. So it also shows how to optimize when only one contender, like for that specific workload, this may be good, and this shows it clearly. See if you can puzzle through the rest of this real world lock to understand how it works. So do it to become master of Linux knocking. So two-phase lock. So one final note, what we did is like we combined the pros again of two seemingly unrelated concept and make it a hybrid, right? So the Linux approach has the flavor of an old approach that has been used on and off for years, going at least as far back to dumb locks in the early 1960s, and is now referred to as two-phase lock. So a two-phase lock, realized spinning can be useful, like waiting for one spin and before it yield, right? Particularly if the lock is about to be released. However, if the lock is not acquired during the first spin, second phase is entered, where the caller is put to sleep and only wakens up the lock when the lock becomes free later. So again, if the lock is not acquired during the first spin space, in the second phase, it will put to sleep and only woken up when the lock has been released by that thread. So the Linux lock above is a form of such lock, but it only spins once. A generalization of this code spin in a loop for a fixed amount of time before using Futex support to sleep. So if you want to like more configure it, you can choose to spin it for a certain amount of time before you can put that to sleep. So you can also do that, to limit and more configure it in detail. So two-phase locks are yet another instance of a hybrid approach. Of course, whether it does depend strongly on many things, including the hardware environment, number of threads, and other workload details. As always, making a single general purpose lock good for all possible use cases is a quite challenge. So again, in this lock library, it's still a challenge to provide a general purpose. So it just used in certain contexts, or that really depends on your workload. So again, these locks depend strongly on many things, including the hardware environment, the number of threads, and other workload details. So again, it depends on your workload. So the above approach show how real locks are built these days. Some hardware support in the form of a more full instruction plus in a form powerful instruction, which is the OS, plus some operating support. Sorry, powerful instruction means the hardware uh, instruction, which is the int and other advanced hardware that has been developed, plus some operating support in the form of Park and non-Park primitives of Solaris or Futex on Linux. So Park and non-Park for primitives for Solaris that support that via OS, while Futex on Linux. Of course, the details differ. The exact code to perform such locking is usually high-tuned. Check out the Solaris or Linux code bases if you want to see more details. So let's skip that and talk about some like I/O, the start of I/O devices to get to prime ourselves to the last part, which is the persistent topic. So I/O devices. So I/O is quite critical to computer systems. Of course, imagine a program without any input, it produces the same result each time. Now imagine a program with no output. So what was the purpose of it running? So crooks, how to integrate I/O into systems? How should I/O be integrated into systems? What are the general mechanisms? How can we make them efficient? So how would you integrate input and output onto the systems? What are the general mechanisms, like the low level mechanisms to do so, and some of the higher level or policies? So how can we make them efficient? So this is the system architecture. So the picture shows a single CPU attached to the main memory of the system via some kind of memory bus or interconnect. Some devices are connected to the system via general I/O bus. So these are the classic or the old way of doing this or connecting input and output to the system. So some devices are connected to the system via general I/O bus, which in modern system would be PCI. So here, like or one of its many derivatives. Graphics and some other higher performance I/O devices might be found here. So graphics might be found here. Finally, even lower down are one or more of what we call a peripheral bus, such as SCSI, SATA, or USB. These connect slow devices to the system, including disk, mice, and keyboards. So these are the peripheral bus. These are the general I/O bus and memory bus. So that's how you connect the CPU to memory before. And the lower down is the peripheral, which is the connects slow devices to the system, including disk, mice, and keyboard. So the disk, mice, and keyboard are actually connected in the same bus. So one question you might ask is, why do we need a hierarchical structure like this? Put simply, physics and cost. So the faster a bus is, the shorter it must be. So of course, obviously, the faster a bus, the shorter it must be. That's why these graphics need to be near the CPU to make it fast. Thus, a high-performance memory bus does not have much room to plug devices and such into it. So a high-performance bus does not room to plug many devices and such into it. So it's just this graphics and memory. In addition, engineering a bus for high performance is quite costly. The system designers have adopted this hierarchical approach, where components that demand
high performance, such as the graphics card, are nearer the CPU. Lower performance components are further away. The benefits of placing disk and other slow devices on a peripheral bus are manifold.
So again, the benefits of placing disk and other slow devices on a peripheral bus are manifold. In particular, you can place a large number of devices on it. So the benefits of far from the CPU is that you can place a lot of device, but it's slower. Of course, modern systems increasingly use sophisticated chipsets and faster point-to-point interconnects to improve performance. Figure 36.2, page 3 shows an approximate diagram of Intel's 2270 chipset. Along the top, CPU connects most closely to the memory system and the graphics, of course, but also has a high performance connection to the graphics cards and thus the display. So the graphics card is the display to enable gaming, the horror, and other graphics intensive application. That's the reason why you need good graphics to maintain a good display in gaming. So the CPU connects to an I/O chip via Intel's proprietary DMI. So Intel has actually an proprietary DMI, direct media interface, and the rest of the device connects to this chip via a different interconnects. So this DMI on other device connect to this DMI, proprietary Intel DMI, via a number of different interconnects. So basically, these are the modern system architecture, and these are the classic or old school. On the right, one or more hard drive connects to the system via the eSATA interface. So one or more drives connect to that via eSATA interface. ATA, the attachment in referencing to providing connection to the IBM PCAT. So ATA, the AT attachment is referenced to providing connection to the IBM PCAT. Then SATA for serial ATA. So ATA means the attachment in reference to providing connection to the IBM PCAT. So that's the reason why you have this ATA. Then SATA for serial ATA. So that's the reason why eSATA, because serial ATA. And now eSATA for external SATA, to represent an evolution of storage interfaces over the past decades, with each step forward increasing performance to keep pace with modern storage devices. Below the I/O chip are a number of USB universal serial bus, here mouse keyboard, which in this depiction enable a keyboard and a mouse to be attached to the computer. On modern system, USB is used for low performance devices such as these. Finally, on the left, other high performance devices can be connected to the system via PCIe. So that's the bus called USB bus before, right? eSATA bus, the DMI bus. Within it, we have eSATA, PCIe, and USB bus. And the CPU connect to PCIe graphics bus, which is like before the general I/O bus, and into the memory, which memory interconnect bus. So finally, on the left, other high performance devices can be connected to the system via PCIe, Peripheral Component Interconnect Express. In this diagram, network interface is attached to the system here.
Higher performance storage devices such as NVMe persistent storage devices are often connected here. So again, PCIe, Peripheral Component Interconnect Express. So in this diagram, a network interface is attached to the system. Here, higher performance storage devices such as NVMe or persistent storage device are often connected here.